All right, so I want to pick up in this video where we left off from part one. In part one, we talked about, well, I proved the definite integral, right? And so I want to pick up there. And so just to reiterate, the net area between a curve and the x-axis is equal to the integral from a to b of f of x dx. Remember what that is. That is the total area above minus, minus the total area below. Now, the book plays sort of fast and loose with the word area, and I'm going to try to avoid that. So whenever I'm talking about, when I say find the area between the curve and the x-axis or find the definite integral, I'm talking about net area. If I want you to find the actual area of the, like the actual physical space taken up by the curve or between the curve and the x-axis, I will try to say total area, okay? So the net area is what the integral gives you, okay? So let's talk about notation here briefly. This notation is going to hold regardless of what your variable is. So it doesn't matter if it's x, it could be something like an application problem where you're using t. So it's like f of t dt. You could have something like, eventually we'll use u substitution in these, and so you could have something like from a to b of f of u du. Okay, that notation is fine. It doesn't matter as long as the differential variable matches the function variable. You can compute the definite integral and use all of the methods to do that we're going to learn about. Okay, so I wanted to just put that out there. Let's do our first example where we're going to be applying this definition. And these types of problems that I'm about to show you simply ask you to take an infinite sum and turn it into an integral. So the example here I'm going to give you, m sub k represents the midpoint of a partition. Remember, partition is m sub k being the midpoint of a partition. M sub k is what I used in the proof in the previous video. So that's just the midpoint of the subinterval, okay? And then we're looking from -1 to 3. And what we want to do is write the limit as n approaches infinity of the sum of, starting at 1, k equals 1 to n. And this is our expression in the summation here. So it's 3m sub k squared minus 2m sub k minus plus 5 delta x. And what we're trying to do is take this infinite sum here and turn it into a definite integral in terms of x. All right, so delta x tells us our variable should be in terms of x. And we're going from -1 to 3, so that's our lower and our upper bounds, so our a and our b. Our function is going to be 3x squared minus 2x plus 5. Again, I'm just trying to fill in the pieces here. So a is -1, b is 3. F of x is going to be 3x squared minus 2x plus 5. And the delta x becomes dx, right? Because as delta x approaches 0, it becomes dx. So we can write our definite integral then as -1 to 3 of 3x squared minus 2x plus 5 dx. So you can leave it like that, or if you want to put the function in parentheses, either one of those is fine. In this case, it would be assumed that you're taking the integral of this function and that dx is just that. It's the differential. It's not part of the function, okay? So we've got that knocked out. Let's go back. Sorry, back in my notes, not your notes. Let's actually do a problem. Let's actually solve an integral, okay? So let's get rid of this. Got it right here. And here we go. So we want to solve this integral from -2 to 2 of the square root of 4 minus x squared dx. Okay? And what I'd like you to do then is find the area underneath of this curve, or between this curve and the x-axis. And the only technique we have for doing that is looking at the graph and figuring out what the area is. And at this point, we're just hoping that it's a shape or an area that we know how to compute. So here's what the square root of 4 minus x squared is. It is a semicircle. Okay, so if I sketch this out, and it's going to go from negative 2 to 2, and it will intersect the y-axis at 2. So you get this kind of a curve. And mine doesn't look like it, but it's a semicircle. And so we're trying to find this area here. And that area, because it's a semicircle, I can figure out what the area is, right? If I know the radius, which is 2, then it's going to be half of pi r squared. So I can write this, that the area is equal to 1/2 pi r squared. We know that r is 2, so a is equal to 1/2 pi r squared, which is 2 squared, so that ends up being just 2 pi square units. In other words, we can write this for our answer, that negative 2 to 2 of 4 minus x squared dx is equal to 2 pi. Okay, so at this point, the problems that you're going to solve, the functions that you're given will generate graphs for which you can compute the areas. Just remember that the areas above the x-axis are positive, the areas that are below are negative, and using that kind of reasoning and what you know for different area formulas like triangles, trapezoids, squares, rectangles, semicircles, or circles, you'll be able to answer the problems in this section using just those tools, okay? So what I'd like you to do right now is go to exploration number 1, which I believe is on page 286 of your book. Pause the video here and go try those 9 problems and see how they go, all right? I'm going to give you the answers to them so you can check. If you have any questions on them, please make sure that you ask me, all right? So here are the answers. Hopefully you're coming back to the video now. In number 1, area is equal to negative 2. In number 2, the area is equal to 0. Number 3, the area is equal to 1. Number 4, this is sort of a tricky one. This one, the area is equal to 2 plus 2 pi, and that's because you lift the curve up 2 units. And so actually, I'll just give you a little sketch because this one comes up frequently. Students have questions on it. So here's your curve. And you know, so there's that part right there. This distance right here is pi. That's pi. This distance here is 2. Because this hits the curve at 2. It's been raised up 2. And then we know that this area up here is 2 units. And so it's going to be 2 plus 2 pi. All right. Number 5, a equals 4. Number 6, a equals 2. Number 7, a equals 0. Number 8, a equals 4. Number 9, a equals 0. Okay, and now, like I said, hopefully you went through those problems and you tried them, and if you have any questions about how I got anything, please make sure that you ask me. I'll be happy to explain it. Okay. All right. So last couple things I want to talk about. I want to show you how to do an integral. Well, actually, we'll save that for the third video. So let's call that good for now. That will get you through the first half of the assignment, and then well, I guess it would be part 3 of this section will get you through the last part.